Hey guys, welcome back to the LearnAP Calc series. In this video, we're going to talk about the limit definition of a derivative. So I've been talking about limits, now we're going to apply that to the limit definition of a derivative. So we're going to talk about what is a derivative, what is the limit definition of a derivative, why does the limit definition of a derivative exist, and the alternative limit definition of a derivative at a point. As usual, be sure to leave a comment if you're confused or have questions. You can also ask in the weekly live streams we do every Sunday from 4 to 5 p.m. Eastern, where we answer your questions about AP Calc. Alright, so let's get started. Alright, so let's start by talking about what is a derivative. A derivative can be thought of in two ways. A derivative is the slope of a function, and the derivative is the rate of change of the function. Now, either one of these are correct. They essentially mean the same thing. But when you're first learning, you want to memorize the definition that makes more sense to you. So these are two ways of thinking about it. Now, in math, derivatives are written as functions. So let's talk about an example of a derivative. So we say that velocity is the derivative of position. So in other words, velocity is the rate of change of our function, which in this case is position. Now, a quick note about notation. So if we have f of x, our function, or y equals, so I'll say function, there are a couple ways we can write the derivative of this function. So the easiest way is simply writing f prime of x, and this means first derivative. We'll talk more about second and third derivatives later, but just keep this stuff in mind. This is how you would write it. For y equals, you can write dy dx, and you might also see d dx, and these simply mean the derivative of y with respect to x. So this is the derivative of y with respect to x. So these mean the same thing, but these are ways you might see a derivative written for the first derivative. Alright, so let's talk about the limit definition of a derivative. The limit definition of a derivative is the difference quotient, which I've talked about earlier. Limit as h goes to 0 of f of x plus h minus f of x all over h. So let's consider why this is. So let's say we have some function. I'm going to say y equals x squared. Now, as I mentioned earlier up here, the derivative is the slope of the function. So how do we find the slope of a curve like y equals x squared? Well, I can say that the slope at some point is the tangent line, where I'm only touching the function in one place. So this would effectively be our derivative. Now, how do we find a tangent line at a point? Well, we all know rise over run, so we can sort of estimate it. So if we have point B here, we have point A and point C, we can draw a secant line through A and C and get an estimation of what the slope would be. Now, you would all agree that as I shrunk down the distance between A and C and got them closer to B, I'd get a better estimation. So let's denote this a little differently. So let's say that this point is x plus, this is x comma f of x. And let's say that this point is x plus h comma f of x plus h. And this is our secant line. Well, how can we shrink down the distance between x and x plus h to get a better and better estimate of b? In fact, how do we get a precise measurement of b? Well, we can do this. So if we first write the slope of our secant line, we know that it's rise over run. So we have our rise here, f of x plus h minus f of x. And we have our run, x plus h minus x. I can cancel out the x's, and we can see what I'm left with. I'm left with this. Now, as I said before, if I want to get that tangent line, I need to get h smaller and smaller, because h is the distance between x and f of x. I'm sorry, is the distance between x and then x plus h. So if I shrink that down smaller and smaller, I'm going to get a precise estimate. So the way I would do that is to take a limit as h goes to 0. Basically saying, as h gets infinitely small but not 0, let's evaluate this limit. And that's going to leave us with a tangent line, or a derivative. So that would leave us with the derivative at this point x comma f of x. And so if I wanted it at b, I'd simply put this coordinate here, and then take the limit as h goes to 0 of the difference quotient. So that's why the limit definition of a derivative works. Now, quick note, you might see delta x instead of h, and both are correct. Delta x simply means the change in x. So people use this because sort of delta x would be our change in x here, but I've chosen to use h just because people might think that delta x and x are the same thing. If you do use delta x, note that they are completely different inside of a limit. So again, this is sort of a complex topic. If you guys have any questions, definitely leave a comment and I will help you out. Alright, so I've talked about the limit definition of a derivative, and that will return a function. So if I had x squared and I wanted to find its derivative, I could use the limit definition to get a function. But what if I only really care about the derivative at a point? I want the slope at a point. You can also find the derivative of a function at a point using limits with the following formula: f of x minus f of a all over x plus x minus a as x goes to a. And this will give you the value of a derivative at a point, but not the actual derivative function. So this is useful to know if you only wanted the definition at a point, and this is certainly good to know. So definitely be familiar with the formula there. Alright, so let's do a quick example problem. Find f prime of x for f of x equals x cubed using the limit definition. Now if you remember what I said about notation, f prime of x here means first derivative. So here I'm asking to find the first derivative of f of x equals x cubed using the limit definition. So if we remember, it's the limit as h goes to 0 of f of x plus h, so here that would be x plus h cubed minus f of x, which is just x cubed, and this is what we would do. Now again, as I talked about, we want to do direct substitution first, and here we can see that we get 0 over 0. So this is indeterminate. Oops. We need to do more work. And so here, what we would do is we would actually multiply out our cube. And so what we're left with is x cubed plus plus 3x squared h plus 3x h squared minus h cubed all minus x cubed. So here I can cancel out the x cubes, and I'm left with limit as h goes to 0 of 3x squared h plus 3 3xh squared minus h cubed all over h. Now I'm going to factor out an h from our numerator. Sorry, this should be as h goes to 0. So 3x squared plus 3xh minus h squared. And this is going to cancel, so I'm left with the limit as h goes to 0 of 3x squared plus 3xh minus h squared. You can do direct substitution now, and everything goes to 0 except this 3x squared. So I can find that our derivative here is 3x squared. So if you're left with x's, that is a good thing, but you won't always be. But here we can see that our derivative is 3x squared, because after I plug in 0 for h, this is what we're left with. Alright, so that brings me to today's challenge problem. Find the derivative of x plus 4 over x using the limit definition. The solution to this problem is on our website, learn-ap.com. I'll also include a direct link in the description. If you guys found this video helpful, please like and be sure to subscribe for future content. Like us on Facebook and follow us on Twitter for updates about our new videos and live streams, which we do every Sunday, where we answer your questions about AP Calc. Those are from 4 to 5 p.m. Eastern. Links for that will also be in the description. If you're looking for other resources to help you learn AP Calc, be sure to check out our resource recommendation video. As usual, leave a comment if you're still confused about anything, or also any other comments on the video in general. Other than that, I want to thank you guys for watching, and I'll see you in the next video.